Excellent. Thank you very much, Nick, for your very kind words. Nick's done an amazing job putting this whole thing together, so I think we should actually, let's thank him now. But my job here is to introduce our first keynote speaker. He's a former refugee who's going to talk to us about saving the planet. Many of you will know him best for his work on promoting commercial uses of functional programming, and in particular OCaml, where he in particular led the OCaml Labs team at Cambridge, and he co-authored a book on real-world OCaml. But more recently, he's been working on something quite different. He's become increasingly involved in conservation, and he's actually now the Professor of Planetary Computing at the University of Cambridge. He's also the Director of the Cambridge Centre for Carbon Credits and a member of the Environment and Energy Group at the University of Cambridge, where he works on large-scale computation and sensing for environmental conservation. I'm delighted to introduce Anil Madhavapeddy.
Thank you very much, Sam. Thank you very much, Sam, and in particular for the heroic pronunciation of my last name, which was even better than I myself could manage. And it's a pleasure to be here and to see so many old friends and to make new friends. And as Sam mentioned, it's traditional in the keynote to talk about a past body of research and to look back and to contextualize it for the bigger picture. I'm not going to do any of that. A couple of years ago, I decided to take a leap of faith and just pivot my research around some of the big crises facing the planet right now. And as many of you will be aware, there's a huge crisis going on at the moment with the amount of greenhouse gas being emitted into the atmosphere, causing a steady warming effect. And we haven't yet peaked in the amount of emissions being released by our anthropogenic effects, but that's not the only problem. In addition to all of the emissions going on, we're also facing a huge amount of biodiversity loss. So while the UN set up a series of protocols in the 90s based around the Conference of Parties, the COPs, which you might have heard of for COP'26 and 27 just finished in the last couple of years, we've also had similar ones for biodiversity. And in the case of biodiversity, there's been a relative average decline in the number of regularly counted species by something like 69% in the last since the 70s. So there's a huge precipitous decline in the diversity of the natural world around us. And then we also have this problem of desertification. So there's an interlocked system of problems, which mean that the amount of groundwater we're using up and the access to drinkable water is also under deep threat. And there's another United Nations Conference of Parties to deal with that. And we have, as a species in the past, fixed these things. So, for example, the Montreal Protocol is one of the most successful international protocols in human history to deal with the ozone layer having a massive hole in it. But the problem in this case is because we have these interlocked series of problems that any one solution tends to have a cascading side effect somewhere else. So most recently, a good example is sulfur emissions from shipping. So this is responsible for a huge amount of pollution coming from international shipping. It's a really acidic, bad pollutant, and the EU put some legislation in 2020 to curtail it from being allowed. And so this is really good news for the world in one sense, because this graph just shows the megatons of sulfur being emitted by shipping, and there was a drastic decline, which is good news for biodiversity and astropic acid rain and so on. But then, if you measure the global warming of the world, sulfur is actually a cooling agent. And so stopping pouring that sulfur in the atmosphere had the very likely effect of causing global temperatures to also spike. So this year has been a particularly bad year, and we're several standard deviations away from the expected norm. And this is, as of a couple of days ago, the average global temperatures recorded, which you can see are really far outside where we should be at this point in time. So we need to figure out how we can possibly put all of these different pieces together and try to make a more unified model where we can take some action and try to have some measurable way of fixing it. So here we are, we're computer scientists. love trees a lot. And we really, really want to make sure that we can play our part in helping to address this particular crisis. The good news is that we have more agency than ever before in human history to make sense of the state of our planet. So satellites have been launched steadily since the space age began. They give us access to global, real-time, and highly multispectral data, not just the visual range, but also lots and lots of frequencies outside that. And we have an incredible amount of data that we've been gathering over the years to let us know how we're doing. And it's obviously really hard launching these satellites. You've got to shoot them up into space. They've got to not explode. They've got to orbit around the world, and then they beam back their data. And where we're stumbling is not there. We're stumbling in the fact that there's so much data coming back that we don't know how to process it and turn it into meaningful results, keep track of what's going on, and then give this to policymakers so that we can engage in behavioral change. And this is the weirdest place to be faltering after we've gone to all of the effort to put these things in the sky. And this is clearly somewhere where we as computer scientists can actually have an impact. And so this gave me a little kind of edge into where we might actually contribute. And so what I'm going to try to do in this keynote for the next 40 minutes or so is, first of all, give you a sense of some real-world problems and research that I started engaging in about how to quantify the health of the world's tropical rainforests. And then the goal of this is to give you a sense of the kind of problems that we face when trying to make head or tail out of satellite data. And then talk about how we actually apply functional programming techniques to dramatically improve how the operation of science happened in this particular space. And along the way, it's been a fruitful couple of years in terms of identifying new research challenges, and I'll talk about that and hopefully spark off some conversations for the rest of the conference. So, tropical forests. Quick show of hands, how many of you have ever been to a tropical rainforest? How many of you have seen it? So I count maybe 1 in 10 of you have been there. It's some of the most beautiful land on this planet. It contains about 2/3 of the world's terrestrial biodiversity. Lots and lots of different species have been recorded there, and it's mainly around the equatorial belt of the planet. But the bad news is that because this tropical rainforest doesn't really have that much value outside hosting a whole bunch of biodiversity from the perception of an anthropogenic human activity, it's been deforested steadily and dramatically since the 1970s. So this set of 4 plots show us the forest cover in Borneo, and in 1973 it was a heavily forested area, and then over the course of the coming decades, it has been deforested and degraded until just a shell of the tropical forest remains. We can still regrow it, but it's really been used up. And it's primarily been used up for agricultural purposes. So this land is being converted in terms of land use from undisturbed forest into often agricultural land for example, for palm oil or coffee, cocoa, cattle, or soya. And so we need to come up with mechanisms by which we can protect these forests. And one primary mechanism is by finding alternative sustainable livelihoods which give the local people who have been cutting down these forests alternative livelihoods, and making sure that sustainable finance provides a sufficient incentive to switch to these alternative livelihoods instead of actually going for the immediate profit, for example, of cutting down the forest for palm oil. And to give you an example, the Gola rainforest in Sierra Leone has had a very successful project since the turn of the century, where they grow sustainable cocoa within the rainforest and use that and market that in order to provide alternative livelihoods to the people in the region. And this is then sold by the RSPB. You can buy this chocolate, highly recommend it. It's all I eat these days. And it provides lots and lots of benefits to across the board for things we're worried about with respect to the crises I outlined earlier. So the trees are preserved, so there's carbon sequestration. These are old growth trees that have been around for hundreds of years, so they have vast amounts of carbon in there, the lungs of the planet. It improves local livelihoods because there's this stream of sustainable chocolate that can be sold at a premium. It preserves biodiversity because these old growth forests are not being cut down. Tree planting as an alternative does not preserve biodiversity in quite the same way because these are ancient ecosystems that have been around for a long time. And also, the rainforests emit lots and lots of water, so it battles desertification. These projects are a win-win, all in all. But the challenge we have is that we don't know how to assess whether or not this intervention has been effective or not. So the Gola Rainforest Project has been set up. It's a highly complex project with thousands of people involved in Sierra Leone. And the classic method by which these are assessed is that when the project is started, they declare what they think is the background rate of deforestation for that particular region. And so this is a manual process. Some experts kind of drop ship into Sierra Leone and they declare that. And then the goal is to create a counterfactual, to say that how much better is this intervention doing versus the background rate of deforestation throughout the rest of the country. And that difference tells us a measure of how effective it's been. But this is hugely inaccurate over decades because, first of all, you're declaring what you think the background rate is, and of course everyone will vary in their estimates. And that makes projects incomparable to each other because we're using different baselines. And so ideally, we want to find a better way of doing this that doesn't require so much manual, on-the-ground checks that happen only infrequently. So it's typically once every 5 years or so. And this is where satellite data comes in. So we should be able to, by definition, spot these rainforests from space. Unlike an urban region, every tree canopy is more or less visible from space. And we should be able to use this to generate an entirely new global metric to assess everywhere across the planet, across the equatorial belt, just how effective these forest preservation efforts have been, with the goal, obviously, of halting tropical deforestation in the next decade. And the way that we do this is by repurposing satellites that have already been up there in the sky. So since about the 1970s, 1972, when NASA launched Landsat, we've had a series of Earth observation satellites up there in the sky. And we have roughly around 10,000 known satellites, obviously lots of spy satellites we know nothing about. And there's about 900 of them are regular Earth observation satellites whose only goal is to send us back data. And you can imagine how much data that is, given they all have lots and lots of different instruments and so on all over them. And what they do is that these things sweep across Earth, and they're taking measurements, and they form orbits that spiral around the planet, and they gather their specific instrument set of data and they beam them back to Earth. Now, of course, this is not what you see when you look at a map. There's lots of post-processing that happens to remove clouds, for example, to take multiple passes and stitch it all together into a coordinate transform that gives you a more familiar kind of map-based interface. So the things you see are composites after lots of processing over these satellites. And then we can use that to start reasoning about properties of places on Earth. So since about 1990, there's been something called the Hansen dataset, which measures the rate of deforestation across the planet. And this is an animation I put together across the Amazon part of South America. And you can see that there's these frontiers of orange that are deforestation that is sweeping through there. So something like 20% of the Amazon is now secondary forest as a result of deforestation. So already the satellites are starting to give us a snapshot of the scale of the problem. So at least we can identify how bad things are before we can start to identify solutions to fix them. So this is really urgent that we get through this. Luckily, the most insanely science fiction thing I've ever seen also helps us to get more accurate. The Japanese launched onto the International Space Station an instrument called JEDI, which is essentially a LiDAR, which is one of those terrestrial lasers that you see in self-driving cars, for example, except they're massive and they're in space, and there's 3 of them. And what it does is it measures surface topography. So this is a very different instrument from the spectral kind of visual or near visual wavelength satellites that were there before, and it lets us build another alternative data set. And so this data set is the surface of the planet. So this starts to tell us really accurately how high anything is. And so this, in combination with the multispectral results, start letting us estimate the world's above ground biomass, which is to say how much biological tonnage is there in this particular part of a forest. And so we're putting together lots of multimodal results in order to figure out for a particular range of the planet exactly what is there. So we're starting to see now how we can start to quantify what was a really kind of analog project starting to do with cocoa in Sierra Leone. And what we're trying to do is we're now trying to take the satellite data, and we're looking at the percentage of forest area. Our goal is to maximize that. And then we have projects which start and end in a given year. And what we're going to do is to come up with some metrics, and these metrics will essentially measure what I call the additionality. I'll define these shortly, leakage and permanence. And once we have these quantified, our challenge is then to apply these across the world in as easy and as reliable way as possible, and to come up with justification for how effective all of the individual alternative livelihood projects are around the world. So the first thing we want to measure is additionality. There's lots and lots of forests in the world. We can't directly pay to protect them all, much as we'd like to. And so what we want to do is to create a counterfactual that says, if we didn't do anything, this is the direction the forest would have gone in. But if we do something, then there's a divergence, there's an intervention, and there's hopefully less forest being cut down. And so the additionality is the sum of the differences between the forest stocks during the duration of the project itself. And the way that we can measure this using satellites is actually really similar to how we do drug trials, because we can say that we can create some control spaces, and we can use those control spaces to measure areas that should be as similar to the project being intervened, but actually being deforested because they're outside of it. So let me show you what this looks like. So this is a system we built for Sierra Leone, for the Gola Rainforest. If I just zoom out, you can see that we're off the coast of Africa. And the first thing we do is we define the project area that is the protected part of the Gola Rainforest. So this is a really interesting part of the world. It's between the border of Liberia, where most of the rainforest continues off over there to the bottom right of the map. And then there's the rest of Sierra Leone, which is very, very built up. And what we're going to do is we're going to try to use satellite data to sample different parts of the project area that is in green. And then we're going to identify, by doing a huge search across these maps, where there are similar trees of the same elevation, the same biomass, the same distance from roads, and we're going to pair them all together. So we're going to say, well, let's find control points that are as similar as possible to the areas being protected. And then we do this individually for every single part of the satellite map. As you can see here, if I click on different matches, there's different elevation, slopes, accessibility to roads, which is a big deal for deforestation, and above ground biomass, which was calculated from the combination of the satellites I mentioned earlier. And then this lets us actually then build up some functions that say, well, let's add up all of the forest mass against both the control, which is outside the project, and the actual project itself. And the x-axis here is plotting by year. This is real data from 2012 to 2020. And then the y-axis is the percentage of forest. And you can start to see already that the blue, which is the controls, are deforesting at a higher rate. So there's clearly some benefit to the forest run by Gola, because the areas that are being matched outside all keep changing. And then what we can do is, because we're just doing this over satellite data, we can just say, hey, let's just blanket the entirety of the project and get a statistically accurate measure, which takes into account spatial autocorrelation and all kinds of confounding factors, but that gives us a graph that actually tells us what the additionality of the project is. And in this case, it's 2.2% for the curious. It seems small, but that's the huge amount of forest being protected. And it gives you a sense of how we can start to do the calculations that we need to do without actually having anyone on the ground going there and measuring individual trees, which is a state of the art at the moment. And so there's lots and lots of variables being used here, so 50 to 100 variables, which has all kinds of things like soil models, and we want to get it as accurate as we can with finding these control points. But because we're using satellite data, we can just do that. It's just a matter of lots of searching and statistical tests across that part of the world. But then it's not enough to just measure positive interventions. You also have to measure what is known as leakage. And leakage can be thought about as negative externalities that happen as a result of an intervention. So if you intervene in for example, a coffee plantation, the global demand for coffee does not drop, so somewhere else is likely being deforested to satisfy that demand. And so we also want to figure out and make sure that there isn't just an immediate local shift in terms of the deforestation just happening next door. And there's other various global equilibrium models to figure out if it goes to different countries. And so in this case, we apply the same algorithm that we did before, except instead of searching across the entire landscape, we just search in a buffer zone that is nearby the project. So we just say, let's just look around the project area and look around this little leakage belt that is a buffer around that particular part of the project. And this should tell us whether or not the deforestation is just increasing locally because they're just taking money for one thing and then spending the deforestation income somewhere else. And you can see here, it is like searching for a needle in a haystack. So over here, those tiny little things in the middle are the actual forests that we're checking for a particular part of Sierra Leone. And then this is the 5-kilometer buffer zone. So we have to be really quite accurate in terms of how we assess different forests and trees to check for leakage. But it is just the right resolution to make that possible. And then we also want to make sure that the permanence of these things, because trees don't live forever, and after the project finishes, that this actually has a story for how long this carbon will be sequestered. So unlike putting stuff into the ground, we also want to keep an eye on the project actually doing what it does even after the end of the intervention itself. And obviously, the only way we're going to win this entire fight is by governments stabilizing land use. So there's a promise at COP26 that we would stop deforestation through legal methods by 2030, but well, it's 2023 now, I think, and deforestation continues to increase. So really the most likely outcome of these interventions is that once the money flow stops going in there, quite reasonably, they revert back to the things they were doing before, and then the palm oil manufacturers or soya manufacturers just cause the deforestation to drop back to what the counterfactual was. And so we can also come up with algorithms to try to measure what the value of holding that emission back for a few years is. Because there's clearly some value in not deforesting for the next 10 years, but it's not as much as not deforesting for the next 100 years. And we apply lots of discount factors in economics to do that calculation using the real satellite data of what is being deforested as a baseline to give us the accurate projections from. There's a paper coming out in Nature Climate Change on this next month for those who want to see the details. But for the purpose of us trying to encode algorithms, well, you've taken a whirlwind tour here through what we're going to do in terms of calculating something from this. And we have some functions. And these functions are given to us by the scientists. We say we have additionality, we subtract the leakage, we divide it by the ratio of expected permanence, and then we apply lots of satellite data. And we should have something that can be used to help save these tropical rainforests. So now we have something where we can absolutely dig our functional teeth into and try to say, well, how do we just make this happen as reliably and as quickly as possible? Now, the scientists that we talk to, they really, really know what they're talking about when it comes to trees. But then we sat down and actually looked at their workflows for how they were actually doing their science. And it was not the most ideal situation. So they would be hacking in R, for example, on their laptops, using curl and wget to fetch things. They then upload something to Google Earth Engine, which is a hosted platform for these things. And then after a little while, they'd wait because there's resource limits in Earth Engine, so they would maybe create 20 accounts, get banned by Google for breaking the resource limits. Then eventually download gigabytes of data from NASA, and then they'd run it through a C++ forest simulator and compose these things in, run out of memory, and then before you know it, they've forgotten what they did in the first place because they've just been distracted by all of the kind of intertwined problems. And it just took them years to come up with the simplest analysis. It was not a fun experience for them to actually do that exploratory science. And it was hard to reproduce, data sets kept changing, everything was going wrong. And there was also multiple different cloud platforms. So the question is, well, could we just sit down with them and design a more functional approach that would just improve this situation and just make it better? And the answer is obviously yes, otherwise it'd be a very short keynote. And the structure of this pipeline should come as no surprise to anyone here, because we've got a whole bunch of data, we want to ingest it, we then want to run some data transformations over it, and we want to make sure that it's traceable as you go through those transformations. We then want to do some analysis, so the algorithms that I outlined earlier, and then we want to iterate. We want to make sure that we can recompute based on our changing inputs, and then we should be able to then publish them and actually have something permanent. And a lot of these words should be triggering happy thoughts in a lot of you right now, because this is the kind of problem space that we solve all the time. And the challenges that they gave us when we just talked to them were simply the ones that you might expect from having to deal with lots and lots of these kind of intertwined data sets. There's lots of scale involved. They had to recalculate and rerun their scripts from scratch all the time. They couldn't reuse other people's results because they'd forgotten what they shared online and what they had in, some secret, some not. And just generally, it was a very mutable environment. So it was very, very hard to figure out exactly what's going on. So let's now spend a few minutes just focusing on how we might be able to fix this by applying some functional programming. So the first thing we did was we sat down with them. So instead of just telling them that go learn a camel, which I might tell my undergraduate computer scientists, but definitely not a bunch of ecologists, we actually sat down with them and started to try to figure out, well, given your data flow, how do we restructure this computation into something that might look a little bit more tractable for applying some good properties to? And the first thing that you want to do in this situation is to just separate the data that is coming as inputs. It's very large and unwieldy to manage. And then you want to structure the actual graph of computations that you will then apply over these things in order to get to your eventual output. And this seems sensible, it seems fine, but then the voices in my head started speaking to me. And this looks very much like a conventional application of building data flow graphs using monads and applicatives as we do with build systems and many other domains. So that's exactly what we did. We just said, well, okay, let's build their trust and start to write these analyses down, and started building a DSL that essentially composes transformations over geospatial inputs. And this is called O-Current, written by Thomas Leonard, who's somewhere in the audience. He's sitting over there. So talk to him if you'd like all the details you want about how it works. But at a very high level, this is some camel code. And you define a series of terms, nodes of computation, that can happen in parallel using an applicative. And the use of the applicative should be fairly familiar. We define a term. It's augmented with labels so that we can actually build UIs from it. Then you can run maps over them. You can create pairs, and you can just do parallel application. And so this let us express how the base of the setup would happen when it comes to encoding the algorithms. And then sometimes you just add some extra syntax. So there's nice little let binding overrides in OCaml that mean that we can make the use of these transformations just look like normal let bindings, write them in direct style. And then after that, you need a little bit more expressive power. So those applicatives are only enough to express static data flow graphs, but sometimes you want to look at the result of a computation and then decide what to run in the pipeline depending on that result. And so this is where you need a monadic bind in order to depend on the result of a previous computation. And this is then just expressed directly in the DSL as well. So the only real difference from a conventional system is that it defines enough metadata such that it can also render a user interface for it as well, so that you're not just describing the analysis, you're also building lots of tooling around it to visualize exactly what's going on there as well. And then you have to figure out how to get all of these scripts that they've written. And so we work with them to say, well, we're not going to modify your scripts, that's your science. And all we ask for is that we just work together to eliminate side effects like all of the built-in downloads and all the stuff happening there. So we just help them delete code. And we found the essence of the code and just said, given a well-defined set of inputs and a well-defined set of outputs, how do you just run the script in a pure way? And then we wrapped all of that into nodes in this data flow graph by writing some OCaml code. And then we could just start to express, for example, how to run some Python scripts. And you can very precisely declare its inputs and outputs. And this is sufficient to build an isolated container namespace, so you can just run that code in a reproducible way, such that if you give it a certain set of inputs, it would always give you the same outputs afterwards. And we wrote hundreds of functions to wrap lots of scripts, and it gets faster as you do more of it, because that's just how programming works when you can reuse stuff you've done before. And then we can actually start to implement the algorithm that we talked about. And the algorithm that we talked about is that we want to write down that additionality minus leakage over permanence part of it. And we can do that now simply by using all the terms that we defined and earlier on. And we can just run a tropical moist rainforest project. And then we can say, well, fetch me the above ground biomass from the satellites. Find me some matching pairs for the satellite matching that you saw earlier. Give me the additionality results, give me the leakage, and give me the permanence, and then give me back the final result. And so the execution engine around this can interpret this DSL and just make sure that just runs on a cluster, runs locally. It just takes care of making sure that it can fetch the data and get you the result that you want. But in addition to also just getting the result, it can also synthesize a user interface. So if we look at an example user interface, then in this case, here we have the data flow graph where you're reading a project, is just executing through as it runs the evaluation. Then it drops into a parallel mode where it fetches lots of different countries and matches and so on. And anytime any of the jobs finish, you can actually just click in an edge and they can see exactly what the intermediate results were. So they can see, for example, oh, this is actually a project that was running on, what was it? On Indonesia and Malaysia, around that belt. And you can download all the intermediate statistics around it. You can also then say, well, okay, so that's given us some data about that particular thing. What exactly happened for this run? And so when you look at this run, this is still a work in progress interface, but you can see all of the low-level pieces that went into it, from cloning the precise hashes of terabytes of data, fetching lots and lots of different pieces, and making sure that we had deterministically installed every last thing. So we use Docker for this, but you can also imagine using Nix or any other purely functional pipeline. And this then gives you the ability to make sure that at every point in this pipeline, you know exactly what is going on. And then, because we're running this over hundreds and hundreds of projects worldwide, well, it becomes pretty easy to just zoom out, look at the different projects, and then start to build more and more elaborate user interfaces where you can summarize the results of running in a pipeline by just building interfaces that can do that. So this interface itself is 3 weeks old. So, but it was a very quick interface that we could build just to unblock the various ecologists who are doing their job there. So this is a nice result, because just building this DSL radically changed the approach that they were taking to their scientific method. It gave them a sense of structure because it tracked all the transformations and generated results. So they didn't have to write the OCaml code to do all the applicatives and monads and stuff. We wrote that for them. But they saw the results because they just saw that we could quickly take this data and assemble it into a pipeline and give them the results that they're waiting for, and then they could drive the user interface themselves. So we didn't go to evangelize, rewrite everything in OCaml or Haskell, but instead tried to build a more friendly environment using these languages, such that it would solve their immediate problem. Of course, that's for now. We do have a Skunkworks project to rewrite everything in OCaml, but that could happen after the more critical science has been finished. And the key thing about this is that the pipeline works both locally and globally as well. So it provides them with an independence of resource usage. They're no longer tied to one cloud provider. They no longer have to depend on just Microsoft Planet or Azure or Google Earth Engine. They can actually just use local resources and university compute clusters to make it all happen. Interestingly, one of the big blockers was how to manage memory. So, and this caught me as a bit of surprise, because normally you're worrying about multi-core parallelism and how to deal with efficient parallel dispatch. But the biggest problem these scripts are having was when you're dealing with terabytes of data, the Python scripts would just run out of memory. It doesn't matter how many cores you have. If they're just allocating a huge amount in their GCs, we have very little kind of observability into that part of it. And then finally, from their perspective, they could use this to systematically do sensitivity analysis across millions of parameters, which they simply could not do before. So this is unlocking the ability to do new analyses that they simply discounted because it was so painful setting the environment up before. And they've already been getting going with this and starting to do lots and lots of good work there. So this was an initial success. We thought, oh, that's really good. And so our pipeline started to get some green in it. So we're starting to solve some of the problems. But then something unexpected happened. So we built this pipeline for the purposes of checking the health of tropical moist forests. And then a whole different group in the same building showed up and said, hey, we want to figure out how to measure the world's biodiversity. And okay, I was like, okay, that checks off one of the crises, so I should help. Biodiversity also very important. What is biodiversity? Well, it's really complicated. With carbon, you're measuring basically the weight of something going into the sky. With biodiversity, you're measuring what is the probability of extinction of humanity, for example. Anyone? Shout it out. One, right? So what's the probability of extinction of humanity over a time period? So less than one, thankfully. And then you have time, and then you have space, because you want to bound that by a region where you want to measure biodiversity. Then you want to stack in the difference of probability of extinction, because you're having an intervention that will hopefully make them go extinct less often. And then you want to stack hundreds of thousands of species. So it's just a really complicated thing. But the observation was that they could reuse lots and lots of the data that we'd already wrapped for the purposes of the carbon project. And so they'd heard rumors about the system and thought, let's have a go. And then this biodiversity was a whole different ballgame, but we went through the same process and we started wrapping it. And I thought you might just like to see some of the results of exploring this interactively. So this is very much cutting edge science, but they needed to not only handle this extremely complicated metric, but they had to explore it. And so what they used the pipeline for was to focus on different parts of the planet to take different subsets out of the hundreds of thousands of areas of habitat of species around the world, and then focus on particular ranges of taxonomies, and then try to visualize it in order to look at specifically what ecological interventions could happen there. And they did this over hundreds and hundreds of different variations. So it had billions of tiles, lots of hexagons, and so on and so forth. And so what was happening here is that, first of all, the yellow represents fewer species, and then the darker portions represent more. So obviously in the Amazon rainforest, lots of species. And then they were kind of exploring these things, trying to see, well, where do different parts of the species setup happen? There was a weird yellow spot there. It's a city, so you can just flip layers. They just dynamically select the layers that they want. And then, well, they can turn the axes around to stack the number of species per tile. And then notice that everything just looks weirdly flat, because this means that we're using the wrong scales for the measurement. So we need to tweak our results. So then switching back to the other axis mode, and then dropping into a detailed part of the hexagon, and then trying to figure out exactly what kind of ecological interventions they want to make there. So this whole thing is work in progress science, because they're trying to just understand exactly how they can compose all these different data sets and try to figure out what is worthy of taking forward into future analysis. So the next thing that we discovered was that having an extensible pipeline like this in this DSL was extraordinarily valuable, because all of the previous functions that we've written in the DSL represent science, and science at different stages, and just applying that function and then adding more functions, they just let them extend the set of work that they're doing quite well. And so now where we are is that rumors have spread now exponentially throughout the various parts of the Cambridge Conservation Institute, and there's lots and lots of people just banging on the door trying to write stuff in this DSL in order to have a go at encoding their stuff, because everything that gets added to the library just means that it's more and more useful for future endeavors. And so this absolutely enables exploratory science, and lots of the intermediate results are really, really useful. Just like it's useful to see intermediate paper drafts, the same holds true for the entire pipeline of computations across these bits of satellite images. Even if they don't make it into Nature or Science, lots and lots of data there. But then the next surprising result was data versioning, because, well, we've solved the core of it with this DSL, and it's given us a fair amount of data, and we can figure out what to do with it. And then I turned my attention to these terabytes of satellite data that was just sitting around and being ingested. Because how hard could it be, right? Terabytes, it fits in my laptop, not a problem. And when you start to look into these in more detail, you observe a few interestingly unique things about the way that these satellite image formats work. Firstly is that they've been going since the 70s, so there's lots and lots of different file formats and weird quirks, and there's, as I showed you, thousands of different instruments that have launched. So there's a whole different ecosystem of how to figure out exactly what the meaning is behind these file formats. And then spacecrafts come and go. They burn up in the atmosphere after a decade or so. For Landsat, there's been 9 independent launches and since the 70s, so they're just different every time. But the key thing is that we don't have the luxury of just eliminating all of the previous results because the new satellite is launched. We need to still assign meaning to historical data, because we're trying to look at trends across decades. So we now have to figure out how to deal with the fact that the quality of data is just changing every year. And there was another kind of weird result just kind of came out at us. So assume that we're doing this forest exploration, and we want to say, well, we're going to pick a baseline of 2020 to figure out how well we're doing for forest protection against that particular year. And there's something called the GRF dataset from the EU. It uses lots of satellites, and it calculates the forest mass that I described. And it goes from 1990 till the present day, and this is published annually by the team, right? It's a really good dataset. But then if you ask it, what is the forest cover in 2020? It varies significantly depending on when you query it. So if I show you here a little differ that we built for this purpose, so where we're in Indonesia over here. I'll just zoom out to show you we're in Indonesia. Lots of beautiful rainforest over there, and then we can start to plot the actual forest cover in this area. whose interpretation of meaning has changed over time. But for us, we need to know in our pipeline, when exactly did this thing happen? So it's not enough to say, I'm version controlling the 2020 dataset. You now have to pick an additional matrix of, well, this was calculated in 2018 using this particular algorithm. This was calculated in 2023 using these datasets. And so now we have to do a transitive walk of all of our dependencies across all of our analyses and make sure that they're consistent with the datasets that they're using. And we have a paper under preparation that just shows that lots of results published across the entire space have significantly varying results simply because they use different epochs of datasets across time. And so absolutely controlling and specifying and understanding that uncertainty will, we think, make a big difference to the accuracy of these analyses in the future. Because we're not saying, don't upgrade your data. We're simply saying, we need to understand what the diff looks like every time a new data input comes in with a new algorithm. So trying to bring everything under this nice structured set of control. And so the answer to that is actually pretty straightforward, because we're trying to say, hey, just snapshot the data as it comes in, use fancy file systems and container technologies and so on. But we can do this because we have a pipeline that controls all the inputs and outputs. Remember that the old mechanism was for them to just try to embed downloads in their curl scripts. Here we have a DSL that can declare its inputs and then a mechanism that can download them. And we write polling mechanisms for all of the weird and wonderful ways of fetching this data. For example, from NASA, you just have to poll a random URL. You have to register with some of them, and you have to purchase some license for other things. Then you have CSVs that come from the United Nations, and you have to parse those. So lots of messy data formats to deal with. But it's all achievable because we bought our fundamental architecture under control here. So overall, the pipeline is now in a pretty happy place because version code and data as it comes in, it's quite immutable afterwards. And then the only real problem became, how do we have a low latency feedback loop for this so that it can actually deal with the fact that we're actually trying to do interactive computation. And then, of course, in our functional toolbox, another solution emerges, which is self-adjusting computation. And so Thomas built into OCurrent the core of an incremental engine based around self-adjusting computation. And again, you can see familiar functions over here. So you have changeable values that can change over time. And then you can define computations that can, depending on the values, they can either take a read dependency or they can update them. And then you can propagate the results and you can interface them to external systems. So nothing novel from a functional programming perspective, but extremely useful when you put it in the context of one of these pipelines, because we now end up with a large, scalable, functional, and efficient pipeline that has solved many of the problems that we set out to just kind of have a quick go at when the project started. But across all of these things, they just compose nicely, and then it just leaves us with the front end, which is how do you make sure these are reproducible and publishable, for example, as Jupyter notebooks and so on. But that is a very easy to solve problem once we brought the rest of the pipeline under control. But if you're trying to solve a reproducible development environment when everything else is changing under your feet, it's not a problem you want to go into. So functional programming just gave us a lot of discipline in order to systematically get through and solve some of these things. And then the question comes out to whether or not all of this is maintainable. Because one of the very important things is that we didn't just throw this code over the wall to the ecologists, we made a deal. And the deal is, we will work with you in order to supply all these benefits, and we will keep it maintained and under control for the duration of these projects, which might be decades. I suspect it'll go on for a long time. And it was really nice running this stuff in a normal functional language like OCaml, because a lot of them are just separate libraries. And there's lots of links there. I'll put the slides up afterwards, but you can find all published in the OPAM repository, which is OCaml's package manager, many of the different pieces that went into building this pipeline. Of course, our final product, the thing that is the actual user interface and the executables given to the scientists, is something we build, but there's a huge diaspora of dependencies that are just naturally the self-contained pieces of logic that go into this. And OCaml's huge strength is over the years, how easy it is to cherry pick different bits of code that we use in different projects and just lift it out and refactor it into a new system. And in fact, the provenance of the code is, I've just been writing OCaml code for a long time for lots of different things. And there's code from the Zen virtualization days where we wrote the tool stack in OCaml, from an operating system called Mirage OS, which writes lots of network stack stuff, working in Docker, where we integrated OCaml into container management, and at Torides, who maintains a lot of the infrastructure for the OCaml project. And we deployed lots of these pieces there first as training wheels in order to build releases of the compiler and the package manager, and then deployed it more widely into these more mission-critical projects. Not that OCaml is not mission-critical, but the tree-saving projects were really, really important. So this overall was a really interesting exercise because it's led us to understanding new aspects of ecological science, building an empathy with those teams in order to let them advance beyond the state of the art, let them dream about new things that were possible, all by using reasonably familiar techniques from functional programming. But my job is a professor, so I do have to occasionally publish. And there were lots and lots of really interesting things that came out of building the first set of iterations for them. And I just wanted to spend some time discussing some of the future directions where we think these could go in terms of advances in what we do from an FP perspective, or more generally from a PL research perspective. The first surprising thing I learned was how sensitive the data sets are that a lot of the NGOs deal with. So because these are rare animal sightings collected over decades, they have to be very, very careful about where the data goes. How many people here are into bird spotting, for example? Does anyone, I see two hands go up. Now, there's these extremely secretive WhatsApp groups where sightings of rare birds are basically sent, certainly in Cambridge, because if they publish them on any social media, they will immediately get hunted down or captured or otherwise abused. And this is true at scale. So the data I talked about for the biodiversity metric is hundreds of thousands of species all over the world that are some of the rarest species in the world. One leak of this data that is statistically identifiable to an individual sighting will bring the people looking for economic value from those down, and it's kind of game over. So the thing we're exploring at the moment is how to start building in more of a security model into these DSLs, so that you can, for example, as one approach, take information flow control, start building that into the DSL, so you label all of the input data. You can define decentralized access policies, so that if slightly suspect organizations should never access this result, then they will be forbidden for it. And then the pipeline suddenly becomes a lot more manageable in terms of putting in data that comes from different sources. And the great Cynthia Dwork, for example, who invented differential privacy, just observed that it is possible to have analyses where you cannot distinguish the membership of any specific individual or the departure of any individual in a data set. So by integrating these techniques like differential privacy, we should be able to start answering some research questions. For example, is it usable in data flow pipelines, or is it just a lot of annotations everywhere? Can we make statistical guarantees about the outputs of these things so that you can declassify data later on in the pipeline if it is sufficiently broad and general? And can we still maintain memoization and caching through those? And then there are tens of thousands of these NGOs working worldwide, often on shoestring budgets. And the dream is, well, we built this pipeline, so why not just deploy it across the entire planet? Because if everyone in Cambridge could benefit from this, then it's once we have a security model, we can just give them installations, and we should be able to figure out exactly how to build a cooperative global functional pipeline where all of the results of these analyses are shared and replicated and made slightly more durable over the long course of time. So, looking at the program in ICFP, there's lots of really fun stuff. I see Lindsay in the front there talking about higher order choreographic programming in a few days. And this is about how to build code that stages and is deployed onto a distributed system. I'm very excited because you can see obvious cases where we might want to break up our pipeline and do that kind of approach when you're deploying it onto a random computer in Liberia, for example. I saw one of the coolest demos of a user interface for a programming language, Hazel, by Sarah Somar, and this might be the way that we program the actual non-CS expert layer where you want to interactively explore the data sets. So we've already got a whole bunch of existing published work in this space, but we can apply it to this domain and perhaps add in all the security restrictions and so on that we need. So this gives us a good structure for making that happen. And then, these projects last for longer than the internet has been around. So we've just committed to a tree planting project in Cambridge that will last for 120 years. And the internet has not been around for that long. And data formats keep evolving. The governments themselves are engaging in a huge political shift at the moment. They're moving from analog systems that they understand how to archive these things to digital systems. And I don't think they've quite internalized just how big a shift that is, because it means that you're no longer able to interpret what something meant a decade ago. And it's absolutely critical that we be able to do that. But here at ICFP, we have lots and lots of different pieces of stuff that can help us get towards this. So one of the keynotes by Andreas Rosberg will be talking about WebAssembly, which has nothing to do with the web or with assembly, but is really, really useful as an intermediate bytecode to let us express computation in lots of different languages, so we can start to think about how to archive these things in the context of a pipeline like I described to keep these things running for a long time. Kathleen Fisher has done lots of work on data description languages, so we can define the meaning of what it means to be a file format, such that if you just find it on a random tape drive 100 years from now, we might have some hope of bootstrapping exactly what format it was in and try to pull that together. Our august General Chair, Nick, has built lots of formally specified higher order parsers and unparsers. They're deployed in real code in systems in Microsoft. And so it should be possible to put all these pieces together to try to build something that's a bit more holistic, so that we can actually bring some structure to the absolute chaos that is all of the different file formats from all the different organizations around the world. And this feels like not just an exercise in specification, but an exercise in executable specification, so that we can actually use these things in the actual products that we're building, and to help keep them more maintainable and understand the impact of changes afterwards. So there's lots and lots of exciting research that we can move into once we solve the basic problems in the actual ecological science that is the urgency of the crisis that we have at the moment. So I see some people nodding, some people going, yeah, I don't know. Sounds a bit hippie. I'm not sure this is what I want to get involved in. Should you get involved? Well, it's not all roses. So when I shifted subject matter, just everything changes. So they're all publishing in their Nature and Science journals and stuff. No one cares about SIGPlan. We don't really have a home for many of these pieces of science that fit into both camps. It's not quite novel enough in computer science. It's a bit too complicated, and they don't appreciate all of the stuff I just described. You know, they only care about scientific outcomes. And there's a real opportunity cost in actually building things for people that are used. You just slow down. But on the other hand, though, this is all just noise, because there is a genuine crisis. And so if you care about the outcomes, if you just want to think, hey, I want to make a measurable change in something, you might fail, and that's okay, but at least the act of trying helps quite a lot. It certainly helped me quite a lot, because you feel you want to do something about that as well. So, and it's not just a case of trying, it's also a case of educating yourself about the actual issues involved in the various approaches you might take for whatever you decide you want to work on. It doesn't have to be forests, obviously. It could be everything from carbon sequestration to more sustainable livelihoods for people, but all of them require computer science and data processing at a minimum. And so what we did observe is that many universities are basically setting up these interdisciplinary centers. So if you need to find a home, then I strongly advise trying to find one of those. For me, I was lucky enough to get into the Cambridge Conservation Initiative, which is a building in the middle of Cambridge, where there's lots of different departments. And so you can just hang out, have coffee, and learn about what's going on. So it's a very informal way of having those kind of coffee conversations, which we're resuming again after all of the various lockdowns. And it's really important to build trust with people. So that's why finding someone in your local institution you can work with really helps, because you need to have lots of to and fro's and make sure you're around whenever your code goes wrong, or they're getting a weird type error because they're trying to make a change themselves. And there's just so much science out there to dig your teeth into. So there's whole domains that I haven't really discussed, from numerical modeling, how to build scalable climate models, from agent-based systems, how to apply machine learning to these things. And all of them, obviously, as a basis, require solid programming language support. So I'm very pleased to shamelessly promote a new workshop that will be at Popple in January, which is called Propple, which is Programming for the Planet. And Dominic Orchard and myself will be starting to begin this conversation of how to bridge some of these topics across different communities. So in addition to this week at ICFP, I hope to keep this going so that we can start to build up a little bit of room for people who want to learn, experiment, and then spend the time building up your own local systems in wherever you go. And overall, I just wanted to leave you with David Attenborough, the the building I work in is the David Attenborough building. And when I first got started there, my overwhelming emotion was one of just anxiety, because you just feel like a foreigner in a place where there's lots of such good work going on, and you don't know where you want to contribute to all these really complicated sounding crises. And certainly by the time I got involved, my overwhelming emotion is now excitement, because they took the time to give us areas where functional programming might happen, but also to tell us that now is the time to actually do something with this. So we've talked for many, many years in venues like CUFP and so on about how there's benefits to functional programming, but here we have an audience who needs it right now and can measurably multiply their effectiveness when they go out into the big world and try to draw change. All we have to do is to make their use of computing systems and data processing more efficient, more reliable, more scalable, and more reproducible, and then we've done our part in a big collective engine to fix humanity's impact on the planet. So I'm really looking forward to continuing this conversation with all of you this week. If any of you have any questions, ideas, or disagreements with what I said, just grab me wherever I am. And also, if any of you are going through Cambridge and you want to learn more about this, you're all very welcome to come down and get a tour of some of these areas and see how you might want to start something up yourself in your respective institutions. So thank you very much for your time, and I look forward to the rest of the conference. Thank you.
Thank you very much for a wonderful talk, Anil. Very inspiring. We've got plenty of time for questions, so people in the audience who want to ask questions, please come up to one of the two microphones. We can also take questions online through Discord. Go ahead.
Hi there. Can you hear me?
I can hear you.
Fantastic talk. Thank you so much.
Closer to the mic.
Closer to the mic? Closer to the mic? No? Hello? Test? 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 Maybe? Yes. Okay. You've made a really compelling case for kind of usability aspects of FP, improving some really important problem spaces. I wonder if you've done any kind of formal usability analysis in the style of HCI work,
Yep.
Or if you've considered that kind of thing, if that's something you think would be important or anything like that.
That's a great question. So have we done any formal user studies? The first metric is, are people giving us the time of day? And so we're in a building where everyone's just really, really busy. And they're also, they're quite disconnected. So people just disappear into field trips to look at wombat poo for weeks on end. And there's been more people that we can handle right now. So we're still at the frontier of trying to build reusable systems that are self-service that other people can use. But afterwards, it is really important to make sure that we have satisfied all of the accessibility needs and so on. Now, this is one area where, especially formal studies into accessibility is really important, because they're in the global south where illiteracy is really high, for example. It's really power starved, and often it's network starved. And so the things that we take for granted here simply do not operate the same way. And the way that people use computing devices like phones is just different culturally and technologically. So it is really important. And we will learn by doing, though. So we don't want to pause in order to do formal user studies. Is to get stuff out there, make sure we have ethical approval for obviously any cause no harm, and then continuously be refining our techniques as we go through.
Thank you.
Okay. Let's take a question from online next. So Edwin Toruk asks, for detecting data leaks, have you tried to also use approaches like canarytokens.org? He says he has no affiliation with that project.
I'd say thank you, Edwin. I have not, but I will look into that as soon as I get back to my to my desk.
Okay.
All right. Fantastic talk. Really exciting. You mentioned like new workshops as one possibility for this kind of work, like making it into academia, right? I'm curious if you have any other thoughts for like, how can this kind of work, which I think is really important, like make a bigger presence or like have a bigger presence in the academic world?
So it's interesting you say, how can it have a bigger presence in the academic world? There's one book I read this year that changed the way that I think about all of this, called 5 Times Faster by Simon Sharp. And he makes a case that we have to move 5 times faster in terms of decarbonizing and biodiversity preservation. And how the heck do you change any system to move 5 times faster? And one way to do that is to give policymakers, for example, the right tools that they need to do their job, because they're the ones who have systemic influence over billions of people. And the way that we work is that we tend to publish to other scientists, or we do direct public communication, but rarely to government, for example. It's just not a thing. And so the way I'm trying to cast this right now is that you need to get involved with the heart of the problem and try to influence not just other academics. They're probably the lowest of the priority, but how do you influence policymakers in particular? Because governments around the world are just looking for answers. Now, I had observer status at COP'26, so I saw how all of the negotiations happen in these climate summits. It was literally Post-it notes being passed around and people just kind of guessing what the impacts of things were. Now imagine if you had a real-time reactive system with graphs showing the fact that if you gave this emissions trading here and you gave up this land over here, this is the impact in your country. That kind of intelligence, if you provided to governments, they can have informed, data-driven decisions for the good of their own populations. And so I think that kind of empowerment is something that is really important. We should worry about academics too, I guess, but just one thing at a time. So I'm really focused on how to make these available to the wider world in the first place.
Hi. Hello. All good?
Can you hear
Okay. So I have 2 questions. First, a more general question, and then a specific question. So the general question is, I mean, we know everything really is a compiler, and this project kind of seems to intersect a lot with the recent efforts that have been going on with reproducible builds and things like that. So have you done like any connection with this kind of projects, used any of their tools or produced any tools that might be useful to them?
So reproducible builds are a minimum ticket for admission these days. So all of these tools have been deployed in the OCaml ecosystem itself. Mm-hmm. So every time you submit a package to OCaml, for example, it's put into an OCurrent pipeline and all the builds and the tests happen. So reproducibility is happening simply by bringing our dependencies under control. So I'm hopeful that in the OCaml ecosystem that we do have automated reproducibility checks. And that is just happening incrementally, step by step, as we go through. So it's not 100% reproducible yet, but you can find a large part of the ecosystem, the build tools, do admit reproducibility. We can then use containers and other isolation mechanisms in order to provide the rest of it afterwards.
Okay. My second question is...
Now, can we have, move on, because we've got lots of questions. So, Jeremy, please.
Hi,
can you go back
Anil.
to the back of the queue?
You've obviously been motivated by ecological questions, but a lot of the technical work, what you're talking about, is much more applicable across all of science. So astronomy and economics and things just leap to mind. Are you going to consider those? Can you consider those? Are they welcome at Propel?
So other science is important, but focus. So really goal-oriented and outcome-oriented. So we want to make a measurable difference in this decade to tropical deforestation, so that has to happen. And so everything takes priority over that. And just generally, it's a lot of effort to learn the actual science behind this thing. So, I've learned some economics, but I'm not an economist, and you have to just pick your focal battles. So my hope here is that we're releasing reusable tools, so someone else who wants to look into that part of it can form a diaspora that will actually go off and use these things. And that's where our communities shine, right? Because we are really good at releasing reusable tools. And so if anyone else wants to look at a different area, I believe there's a lot of value to just grab some of these techniques and build on them and cooperate.
Good. Thank you.
All right, great. It was very interesting to see your snapshot of the DSL, and I saw that there were mostly polymorphic functions. So in DSLs, usually try to represent concept of the domain into the types.
Yeah.
And when I was seeing your talk, there was thousands of types came into my mind. So how crazy you were into doing that?
Well, the good thing is that my co-author of this, who wrote most of the DSL, is in this audience. That DSL is written in a fairly normal OCaml style, which is you define module types for the term language, and then you just have functions that are combinators over those. So it's not designed to be kind of a really invisible deep DSL that hides all these things. It's just you're writing OCaml code that results in a value that you can then interpret, and it just happens that there's nice syntactic sugar to make it look like a let binding, and then there's a nice set of combinators that you can just apply to make it look more sequenced. But it's not, the goal wasn't to come up with the ultimate DSL. The goal was to just get on with the actual pipeline and to build user interfaces and stuff around it. We're pretty happy with the core of it, but there's another rewrite coming in, which is to try to remove the need for dynamic data flow and maybe take a more staged approach to things, so that most of the time you don't need the power of a monad, you just need applicatives, but you do need to occasionally stage things so that you know when you've done a little bit of discovery and then you can move on to the rest. So we're going to refine the core of it pretty fast.
Relating to that, I had a question. Did you make use of the new OCaml 5 features? Effect handlers, for instance. I know.
So a lot of the OCaml code, the system makes heavy use of multi-core OCaml and EIO and effect handlers and so on. So we built a new library called EIO, which is just a really, really high-performance direct style thing that uses all of the features of the OS and OCaml. But OCaml itself specifically doesn't use it because it's trying to describe a pipeline. So we don't quite see where effect handlers can hide that construction. But it does mean that every other monad has basically disappeared. So LWT, for example, which is a concurrency monad, is long gone. Async, for example, which is a JSON one, is gone as well. So it means that you just have one monad. And I find monads manageable when it is one of them. And that's where we are right now. So I'm in my functional happy place with that.
Over here.
I'm delighted to hear about the new Propel workshop. I think our community has a lot to offer to scientists in many domains. And in fact, there's a new workshop this Saturday, co-located with ICFP, called DecalMed, Declarative Biology and Medicine. We're trying to get people from this community to try to figure out how they can apply all their techniques and tricks with all their might to biology and medicine. So that's this Saturday here.
I will be there. I did not know about that. That's wonderful. Thank you.
Hello. Very nice talk. I want to ask, are there any competing approaches to functional programming in order to analyze and harness this analysis of geospatial data?
It's a great question. There's YAML and Kubernetes and so on. So there's what cloud computing does right now. And that approach is basically saying that you specify data flow graphs as a custom file format. So if you've used YAML or JSON and so on, I find these things just absolutely impenetrable. So and anytime you look at them, you have to figure out what are the incentives of the people who are pushing the technology, and they're basically pushing you to use the cloud, right? And so everything has to look like a distributed systems problem, and then you have to spin up lots of resources and so on. So we specifically moved away from that because the entirety of the global satellite pipeline fits on my laptop. So it's 2 terabytes. So I have one machine that has 256 cores. It's got 2 terabytes of RAM, and it can run everything as a single kind of shared memory parallel system or process-based system. So you don't need all the complexity and overheads that these systems bring in, and you can also just deploy them locally. So we're really underwhelmed by the state-of-the-art in cloud APIs for serverless and so on. And the functional approach, it just wasn't that much work. A lot of the pieces that we needed were already in place. So we haven't deeply looked into other mechanisms by which we might do that. We just know what we didn't want to do, which is use existing lock-in cloud provider APIs.
We're running into the break a bit now, so I think let's just have one more question over here.
Hi, thank you for a fantastic talk. I am an undergrad here, and there are many others here, part of PLMW and the other mentorship programs here. And as your slides showed, I find we often are some of the loudest voices in these conversations of conservation. How can we, who are inspired by this, immediately get involved in walking the walk?
Cambridge has a great graduate program. It's only 3 years, not 5 years like the US and stuff. Just forget all these other people. Just come over. It's a lovely place. Great pubs. But seriously, climate justice is and youth justice is one of the most important things. We are doing this for generations that will feel the pain. There's lots of youth justice distributed networks around, and they are really, really hungry for technological inputs. So there's actually an internship program called Outreachy, which has been used to get underrepresented minorities from all over the world to apply to tech programs. So one of the things one of my colleagues, Patrick Ferris, and I are working on is to get some of these projects into Outreachy so that anyone who wants to apply, who's in a teaching program anywhere in the world, can actually come in and do that. And then the other part is to get involved with open source as well. So when you're looking for kind of side projects to learn from, just try to apply these things to a local problem that you have. And so often, the way I got into satellites was just trying to analyze there's a controversy in Cambridge about some highways and trees and stuff. And we were just trying to figure out what that was. And then you get sucked into the problem domain more and more and more. So start by solving local problems, getting involved with your peers who are campaigning for actual behavioral change, augment their actual efforts, and then learn how to use the multiplying factor of technology to solve good, positive social issues there instead of well, perhaps less positive use of technology. Ultimately, you have to choose where you're going to work, and I think that the vast majority of my students are all looking for jobs in sustainability and agricultural robotics and stuff, where we can improve how we interface with the planet. So I think this is the new wave of employment opportunities for all of you young people who are looking for them. So you're in a really good place to learn by getting familiar with these technologies and then using them out in the big wide world.
Thank you.
Thank you very much, Anil.
Thank you all.